We'll wrap up with Carolina Uhler from MIT. She will tell us about your dreams may come true with MTP2.
Thanks, Bernd. So when Bernd invited me here, I told him that I don't have anything new to report on hyperbolicity cones. So he said I should talk about anything I like. So that's what I'm going to do. I'll talk about these MTP2 distributions. This stands for multivariate total positivity of order 2. And I've come to love these distributions. We've been working on them for a couple of years now with subsets of different people. And so what I want to do today is tell you a bit about why I like them so much and also tell you about how they are actually related to interesting problems in combinatorics and algebra and in geometry. So let me first define what these distributions actually are. And I'll also make it, at some point, there will be one slide where there is hyperbolicity. And that will actually connect to the previous talk that you just saw. Okay? So let me define what these distributions are. So what is an MTP2 distribution? So it stands for multivariate total positivity of order 2, as I already said. And it's a very strange definition when you see it the first time. So a distribution with density function P is MTP2 if and only if for any 2 points in the sample space it satisfies these inequalities. So if you take 2 points, the density at x times the density of y has to be smaller or equal to the density at, so if I take 2 points, right, the density at x times the density at y has to be smaller or equal to the density at x min y and the density at x max y. So in particular, if you have seen supermodularity, right, if this density is everywhere positive, then I can take logarithms on both sides. And then this is really what you get back is log supermodularity. Okay. So why would anyone care about studying distributions that satisfy this strange constraint here? Well, so they were introduced, and here just a bit of history. Why were they introduced? So they were introduced because it is of interest in probability theory and in statistical physics. So people were studying distributions that are positively associated, meaning that, you know, if you take any random vector and you take 2 non-negative functions, then the covariance is always larger or equal to 0. Okay? So this is a very hard constraint to check because I have to check this for any 2 non-negative functions. I have to check that the covariance function is always larger or equal to 0. And MTP2 is actually a stronger constraint. So this FK, very well-known FKG inequality implies that actually MTP2 implies positive association. Okay, and MTP2 is easier to check. I mean, somewhat easier to check because I only have to check it for any points in the sample space. Yeah. And so this was really the motivation for introducing MTP2, just because it is a stronger constraint than positive association.
Sorry.
Yeah.
Is your domain has to be closed under this coordinate twice?
Exactly. Yeah. So you need like a lattice structure. In general, I will here be talking about Rm. Okay. So this was the motivation for introducing it. So let me now give you a bit of intuition for, you know, what kinds of distributions are MTP2. Okay. And what kinds of properties do these distributions have? So first of all, they have some very nice properties. And let me first give you an example of something that is very disturbing in data science that can actually happen. And I'm sure you've already seen this happening. It's known as Simpsons Paradox. And, you know, since MTP2 is so nice, what I want to say is that Simpsons Paradox cannot happen under MTP2. Okay, so what is the Simpsons Paradox? It's something really disturbing. It is the property that if you have 2 random variables, in this case, you know, the sentence that a murderer gets, and the skin color of the murderer, if you look at this representation of the data, there are more white murderers that got the death penalty than black murderers, if you actually just figure out what the percentage is. Okay? However, I can also look at the data in a different way, where I'm also looking at what the skin color of the victim is. And you'll see that in both cases, it's in fact the case that the black murderers got more death penalties than the white murderers. Okay, so somehow if I look at this representation of the data, white murderers get more death penalties than black murderers. But now if I'm actually looking at the skin color of the victims, then in both cases you'll see that black murderers get more death penalties than white murderers. Okay. So somehow when I'm conditioning on a random variable, and this is Simpsons Paradox, when I'm conditioning on a random variable, suddenly the sign of the association can flip. Okay. What was correlated before becomes negatively correlated afterwards. And this is, both of them are real representations of the data, right? That just depends on how you're looking at it. You might actually get to very different conclusions. And so MTP2 is a very strong form of positive dependence, which says that no matter what you condition on, the sign will always remain the same. So that's one of the implications of MTP2, which is a very nice implication. And in fact, even more, so here are some properties that are well known. So it is closed under conditioning, and we just saw an example before. Okay, so this Simpsons paradox cannot happen. And also it is closed under marginalization. So if I have some MTP2 distribution, I can take a slice through it, and it is still going to be MTP2. Okay. In addition, so it's a strong form of positive dependence, so the covariance is always positive, non-negative. And in fact, when it's 0, it means that they're already independent. Okay, so usually it only goes in one direction. Actually, for MTP2 distributions, it always goes backwards. So these are properties that we know hold for Gaussian distributions. Okay, so all these nice properties of Gaussians actually also hold for any MTP2 distribution. Okay. Now, of course, we can ask, well, since these are properties of Gaussians that hold, is every Gaussian distribution MTP2? That's not the case. Okay, so let me just tell you what it means for a Gaussian to be MTP2. So a Gaussian distribution is defined by its covariance matrix, or the inverse of the covariance matrix, which I here denote by K. And a Gaussian distribution is MTP2, so it satisfies these constraints, P of x times P of y smaller or equal to P of x min, y times P of x max, y. If and only if the inverse covariance matrix is an M matrix, so M Minkowski matrix. So what are these matrices? So it's a positive definite matrix where all of the off-diagonal elements are smaller or equal to 0. So that already tells you it's a super strong constraint, right? When have you the last time encountered a positive definite matrix where all off-diagonal elements are smaller or equal to 0? Okay, so in fact, if I randomly sample positive definite matrices or correlation matrices, even like for a 5 by 5 matrix, not even 1 in a million will actually satisfy this constraint. Okay. So why do I want you to care about it, since you should never be encountering them? So because they actually appear in practice. Okay, so here I'm showing you the monthly correlations of global stock markets, which you can actually find just at this website. So this is how the correlation matrix looks like. So it's already nice, at least all of the correlations are positive. MTP2 is stronger, right? I need to take the inverse and still see that all of the entries off diagonal are actually smaller or equal to 0. And in fact, if I just invert the matrix, you see that it is in fact MTP2. Okay, so just by chance, that I can ever find a matrix like this is like smaller than 1 in a million. But here I am giving you an example, right? And I did not go through a million data sets to find one of these. Okay, so the question is why, right? Why do they appear? And this obviously tells you that this is an important constraint, because I'll give you now another example. This is just in the Gaussian setting. Let me tell you in the discrete setting. Okay, so here is again the definition. What does it mean for a discrete distribution, in this case a binary distribution, to be MTP2? Well, so say 3-dimensional binary, I have to go through all possible assignments of 0, 0, 1, 1, 0, 0, etc., right? And just check that all of these constraints here hold. So for example, I take here as x 0, 0, 1, as y 1, 1, 0. I take the minimum, right, gives 0, 0, 0. I take the maximum, gives 1, 1, 1. And so this is how I just list all of the inequalities. In this case, there are only 9 inequalities that are non-trivial. These are exactly the ones that I listed here.
May I ask you, so this is much weaker than total positivity? Yes?
This is total positivity.
Huh?
This is the definition of total positivity. So this is MTP.
This is 2 by 2 minus. Total positivity is all minus.
Okay, so this is multivariate, totally positive, right? So MTP2 stands multivariate, totally positive. Oh, and you are not saying TP2, so you're just saying TP.
Yes.
Yeah, TP infinity would be all minors. So these are 2 by 2 minors. And why is it 2 by 2? You see it here, right? This corresponds to a 2 by 2 minor. Yeah. So this is a special form. And in fact, an open problem, which is very much open, is how to define MTPR. Okay. So we know TPR, but there is no such notion as MTPR. Okay. And that would actually be very interesting to do, because it should be something on tensors. Right? And so this is really wide open, actually, how to define that in a nice way. So I'm just doing MTP2. Okay, so let me just give you an example of, again, a real data set. Okay, so this is a disease syndrome in pregnant women. Here is the contingency table, right? The 2 by 2 by 2 table. And you see that if you just check all of these inequalities, they're actually satisfied. Okay, so again, it shouldn't happen. I mean, I definitely didn't look through, in this case now, 50 different tables just to find this example. Okay, so the question is, why is it the case, and why should you care about these distributions? So they appear all over the place. And just to give some intuition, why they actually appear, so one can prove that basically anything that follows a tree distribution is MTP2. Okay, so what do I mean by a tree, and why does stock market and phylogenetics, etc., why do they all fit? So stock market data, right, I mean, it's believed that there is a very strong market variable, which is latent, right, which really dictates how the stocks behave. And hence, if one stock goes up, then most of the stocks go up, and then they will go down. They might not go up the same amount, right? But they will all be going up and down together, just because there is this very strong market value behind it. And so that's a latent variable, right? Which is a tree structure, which will point out to all of your stocks down here. Similarly, in the example of this disease syndrome, we have one disease that we cannot measure directly, and we're measuring all of these symptoms. Similarly, in phylogenetics, right, obviously it's a tree. If I look at phylogenetic data, you'll see MTP2 distributions everywhere. We're interested in expression data. There, in the cell nucleus, genes that are close together, they're all turned up at the same time or turned down at the same time. In all of these different kinds of applications, you'll actually get to see MTP2 distribution. Okay, so these seem, although super restrictive constraint, right, that does seem interesting from an applied perspective to actually take it into account. So now let's go a bit more into the math. So I hope I was able to convince you that these are interesting constraints. Now, let me at least connect this to the previous talk. And it will mainly connect in terms of open problems that I will get back to throughout the talk. Okay. So let's see. So now we saw Gaussian and binary distributions. So they are just a special case of exponential distributions. Okay, so binary and Gaussian can both be written as an exponential distribution, namely a density function that is of this form here, okay, where I have some exponential of some inner product. The thetas are my parameters. This is just a function of the data that we also saw in the previous talk. And this a of theta here, this is known as the log partition function, which, in the previous talk we saw different examples, right, of, in this case, hyperbolic polynomials. And I'm just taking the logarithm of these hyperbolic polynomials, which are, in fact, these barrier functions of the hyperbolicity curve. Okay, so these are the log partition functions. And both the binary and the Gaussian case can be written like this, in particular in the Gaussian distribution. So what is this a of theta? Just make sure that this is actually a density so that it integrates to 1. So a of theta, so this will give me a density as long as this a of theta is actually finite, right? And that's exactly the integral that was written down in the previous talk, right? I need this log partition function, or this a of theta here to be finite. And the question is, can I come up with a measure nu? Or, this q of alpha was actually the measure on this space t of x. Right? So that this is a well-defined exponential family, meaning that measure actually has to be positive, otherwise it doesn't give rise to a probability distribution. Okay, so the previous talk was really on, how to define this measure, right, on this space over here, which is the dual cone. Right? So the image of t or your samples will actually be matched to the dual cone of C. And the question about the Riesz kernel was to come up with a measure over here so that this density is actually well defined. Okay, and so that's how we defined hyperbolic exponential families. So these are just exponential families where, this a of theta here is of a particular form, where it's some alpha term times the logarithm of a hyperbolic polynomial. And so now one can ask, so this is just a particular exponential family. Right? And now you can ask, well, for a hyperbolic exponential family, what does it mean to be MTP2? Okay. And so I'll tell you a general result. For any exponential family, what does it mean to be MTP2? And now then the question is, of course, does hyperbolicity buy you something nice? And I don't know. So let me just tell you in general, it's actually pretty nice. So let me take any exponential family. And say this exponential family has a space of canonical parameters denoted by C. Okay. And now I want to look at, in this exponential family, I want to look at only at the MTP2 ones. And I'm asking, how does the space of canonical parameters look like there? So it has to be a subset. So the question is, how does it look like? And then what is nice is it's again going to be convex. So I know the space of canonical parameters is always convex in an exponential family. And in fact, if you look at just the MTP2 guys, they are given by intersecting your original space of canonical parameters with a convex cone. And what is this convex cone? Oh, sorry, there is a D missing here. A D. So this closed convex cone, I can describe its dual very easily. Okay, and what is its dual? Well, it's generated by these kinds of things, like these sufficient statistics, right? Just this inequality that we already know. And I don't actually have to go over all possible x and y's in the sample space, because it's well known that to check log or supermodularity, if you have something, log supermodularity, if it's strictly positive, you only have to check it for any two vectors that differ by at most 2 entries. Okay, so that's why you actually don't have to check it for all of them, but just for any 2 vectors that differ in just 2 of the entries. So this is how the space of canonical parameters looks like. And so now the question is, of course, can you undo something nice? If this is a hyperbolic, if C itself is a hyperbolic cone, a hyperbolicity cone, and now you're intersecting it with this dual cone. So I don't have any results about how this looks like in the hyperbolic setting, but I will tell you about what can be said about this in the Gaussian setting. Okay, so when I'm taking this space of sufficient statistics, as we saw in the previous talk, to be the positive definite cone, and then I'm intersecting it here with this space of sufficient, with this space here that defines my MTP2 cone. Okay. We already saw in the Gaussian case, right? We know that a Gaussian matrix is MTP2 if and only if all off-diagonal elements are smaller or equal to 0. Right? So this cone here is actually the non-negative orthant. So in the Gaussian setting, I'm taking this to be the positive definite cone, and this guy here is actually the non-negative orthant, the non-positive orthant. All off-diagonal elements have to be smaller or equal to 0. Okay. That's how it looks like there. But in general, I don't know if one can say something nice about hyperbolic polynomials. Okay, so what are the questions I want to talk about, and where does geometry come in? So I want to talk about 2 different questions, actually the same question, but in 2 different settings. So I want to talk about density estimation. So it's a very important problem where, I give you some samples, okay? So in this case, in R2. And I don't tell you from which distribution they were sampled, and I want to estimate the distribution from which they came from. Okay, so there are 2 different versions of this problem. So either in the parametric setting, I tell you, for example, they come from an exponential family, or I tell you they came from a Gaussian. And what your job is just to estimate the parameters of this distribution. So in the Gaussian setting, to estimate the covariance matrix, for example. Okay, so that's parametric density estimation. So this is usually easier because it gives rise to a finite dimensional optimization problem, because I just have to optimize over my parameter. Okay. Then the harder problem is the second one, which is non-parametric density estimation. So I don't tell you a parametric family. I don't want to, maybe. Right? If I have financial data, I don't want to. I mean, that's what led to the crash in the end, right? I don't want to assume that it is Gaussian. I want to allow it to have fatter tails. So I don't want to tell you that. And all I'm telling you is, for example, well, I want to do I want to do density estimation under the constraint that it's MTP2. Okay, so that's just a shape constraint. And so I want to just give, 2 slides on this setting, but really mainly concentrate on this more difficult setting. Okay. Just 2 slides, because this could motivate what kinds of results you might be wanting to get if you do actually this whole story with exponential families that are hyperbolic. So I'll just tell you what happens in the Gaussian setting. So let's look at the Gaussian setting. I need to tell you, how do we do density estimation? So in both of them, there are multiple ways of doing it. I will do maximum likelihood estimation. So I want to find the density function that maximizes the probability of seeing the data. So that means I write down the probability of seeing the data, and I just maximize that. Here I know it's Gaussian, and here I'll just do the shape constraint itself. Okay. So now I'll show you just in the Gaussian setting what is the optimization problem that we're trying to solve. Okay, so I have some samples from a Gaussian, right? And I want to estimate this covariance matrix sigma. Now I'm telling you it's Gaussian, I'm giving you data, and now I want to estimate the sigma that maximizes the probability of seeing the data. Okay, so maximizing the probability of seeing the data, well, I can maximize the logarithm of the probability of seeing the data. And that's exactly what I wrote down here. So this is the log likelihood function. This is exactly what will happen if you just, plug everything in. And here, as we saw in the last talk, right, the sufficient statistics were these x times x transpose. So that's this rank n matrix, where n is the number of samples that you have. Okay, so this is the function that I'm trying to optimize, subject to the constraint that it's MTP2. So it's a convex constraint, as we saw in general for exponential families. And for Gaussians, it's just that you are in this non-positive orthant. Now this is a nice convex optimization problem. I can actually write down its dual, and I just wrote it down here. So this is an optimization problem over the inverse covariance matrix. This is an optimization problem over the covariance matrix. Okay, so now the question is, what can I tell you about it? So there are two things that one wants to do when one does maximum likelihood estimation in statistics. So one, what would be nice is I want to get a model that is interpretable. Okay? So what one likes is if I get out something here that is sparse. Because then, if I have this, I can then represent it as a network, and that's kind of the interpretation. I can just, concentrate on these few edges, right? So I would like to have something that fits the data well, but is sparse, so that I get something interpretable. And at the same time, also, the setting that one is usually in is one has a lot of variables, but very few data points. So that means my sample covariance matrix is of rank n, where n is small, but the number of variables, so this is a matrix of size p by p is larger than n. Okay, so that's often the setting one is in different applications. So it would be nice if this problem doesn't blow up, if I have fewer number of samples than number of variables. Okay, if I don't have this constraint, then it's easy to see that this likelihood actually blows up to infinity, as long as S, the rank of S, is not full. Okay, so if I don't have these constraints, then this is completely ill-posed. The MLE, so the estimator that maximizes this, the likelihood is actually, it doesn't exist. So this function just goes off to infinity. So these are two things that I would like to show under these kinds of constraints here. And briefly, that's exactly what we get. So I can look at, since I have strong duality, I can look at the KKT conditions and complementary slackness. You can just write it down. It's very simple. And it says that either, my MLE of the covariance matrix has to be given by the entries of the sample covariance matrix, or otherwise I get a 0. Okay, so why does this already imply sparsity? Well, we know that under MTP2, the correlations all have to be positive, non-negative. Right? So obviously in the sample covariance matrix, I can have negative entries. So in particular, all of the ones that are negative will already imply zeros and numbers. So I will get, so this we already saw, right? Under MTP2, the covariances are all larger or equal to 0. And so that means that actually my estimator is going to be sparse. Okay, so geometrically what is happening, why is it sparse, is I have this cone, this PSD cone, right? And I'm intersecting it to get the MTP2 matrices. I'm intersecting it with a polyhedral cone, which is this non-positive orthant. And now you're doing maximum likelihood estimation, and obviously very often you're going to land on one of these faces, which tells you that you actually get sparsity. So it would be interesting to see, what happens if you do something similar under hyperbolicity, right? So a more general class of exponential families. Okay, so this is for sparsity. Now I also want to show that, this likelihood function is actually well behaved, even if you have very few samples. That this is actually an implicit regularizer. And that's another, tells you again that something very nice is going on in terms of algebraic constraints here. So this was already proven in 2015, but this is like a multi-page proof. And I'm going to give you the same proof just in 2 lines, okay? But actually using some nice, ultrametric matrices. So ultrametric matrices are matrices that satisfy these kind of triangle-like constraints. And they're nice. So what are we in fact going to use is that, well, if you have an ultrametric matrix and you have no 2 rows that are equal, you already know that its inverse is actually going to be an M matrix. Okay, its inverse will have all of the entries, all of the off-diagonal elements, smaller or equal to 0. So how am I going to prove this result? So what I want to do is I want to show that this problem here doesn't go off to infinity if I have here a matrix that is of rank 2, okay, 2 or larger. So how I'm going to prove that is I'm just going to give you a primal and dual feasible point. Okay, if I have that, then nothing bad can happen, right? So that's all I'm going to do. I'm actually going to construct for you a primal and dual feasible point just in 2 lines, okay? And I'm going to do that by constructing an ultrametric matrix, right? Because then I know that its inverse is already an M matrix, hence it will satisfy these constraints. Okay. So let me just do that in 2 lines. So I'm going to start with a sample covariance matrix, and I want to construct to you a dual feasible point. So let me go back. I want to construct a dual feasible point, so all entries have to be larger or equal to my sample covariance matrix. And I want that its inverse is actually an M matrix. Okay, so I'll construct an ultrametric where all entries are larger or equal to S. Hence, I know that the inverse is already going to be an M matrix, and then I'm done. So let me just do that. So I start with S. And what I'm going to do is really just build, so as if you were doing clustering, I'm just going to build the tree that basically fits the data the best. So I'm looking at all of these entries of the correlations as how similar are 2 points. Okay, and I just choose the 2 biggest entries of my correlation. So these are the most similar points. And I cluster them together. Okay, so I build a tree, I cluster these guys together. Then I look at the next similar entries. So that would be this entry here is the next largest one. And now I already clustered rows 1 and 2, or columns 1 and 2. I will cluster 1, 2, and 3 together. Okay, I'll cluster everything together. And I'll replace it by max similarity because I need to construct a matrix that is larger or equal to S. And you just continue like that. I choose the next largest entry, which would be this. I'll cluster these 2 guys together. And the next largest entry would be this. And then the similarity becomes just the max. And that's how I constructed an ultrametric, which is primal and dual feasible. So I know that it's not going to go off to infinity. And I can show if you have 2 samples, then no 2 rows will be equal. Okay, so that's just a 2-line proof of this fact, which is really nice, right? It tells you somehow that the MLE already exists if I just have 2 samples. So that's very different than in the general Gaussian case. So it's a really very restrictive family that really acts. MTP2 acts as a nice regularizer. And you get nice and sparsity conditions for free, as seen on the previous slide. Okay, so now the question is, of course, what happens under hyperbolicity? Can you say something like this?
What about the inverse of the matrix that you constructed? So you have sparsity there in the inverse?
No, that's only at the optimum.
I see.
So now I have a point that is primal and dual feasible, but at the optimum you're going to go to the boundary. Okay, so in general here all of the entries will actually be negative. Okay, so these are the kinds of questions that we like to answer, right? So how many samples do I actually need for at least the MLE to exist? And the next question would be, how good is the MLE? And then also, do you actually get sparsity, and what does the sparsity pattern mean? So these would be kind of nice questions to answer also for hyperbolic exponential families. Okay, so that was kind of the easier setting where I want to estimate the density function, given that, I'm just assuming it's Gaussian, or I'm assuming it's some exponential family.
Question. Mm-hmm. So in terms of promoting the sparsity of covariance matrix, how does the MLE in setting of MTP2 compare to graphic lasso model?
Yes, so it depends, right? So if I just take a random one where I don't assume that MTP2 makes any sense, then in general I'll get super sparse estimates. But even under MTP2, it's actually a very, very strong regularizer. So we experimented a bit with actually make it less strong. So for example, you can make it less strong by just saying that sigma UV has to be larger or equal to SUV minus lambda. Okay, that's how you can relax MTP2 if you want it to be less sparse. Or you can make it sparser if you want to add a lambda. So that's how you can add in also, also another coefficient to make it sparser or less sparse. But really, if my true matrix is MTP2 and it doesn't have any zeros, well, then the MLE will be the true matrix. So then I'm not going to add in zeros. The zeros just come because this is such a constrained space. So in general, I have noise. Even if it is MTP2, I have noise, so these entries will be just set to 0. Okay, so let me now talk a bit about the non-parametric setting. So what do I want to do? So I give you only the constraint that it's MTP2, okay? So why do I need constraints? So if I don't put any constraints on it, I want to produce the density that maximizes the likelihood of seeing the data. Well, I just put spikes, right? I just put spikes everywhere, but that's not very interesting because that just means I completely trust the data and I just put mass onto my data points. Okay, so you want like some kind of constraint that at least says, well, I want to spread out the mass a bit, right? So now, unfortunately, so this is then the problem that I would want to solve, right? So unfortunately, it turns out that even if I have MTP2 as a shape constraint, that's not enough to make it not be spiky. Okay, so if I have here in particular my samples, if I just put mass everywhere here around the band, then this is still going to be MTP2, but probably still not what you actually want to get. Okay, so it's not strong enough to not make it spiky. And shape constraint density estimation is a super active area right now. There are many different kinds of shape constraints that have been studied. And the most studied one is this log concave. Okay, this really makes sure that the density is actually continuous. And so instead of just looking at MTP2, we'll look at MTP2 plus log concave. Okay, so MTP2 plus log concave, we had to start somewhere. Why log concave? Well, it has been studied a lot. And also there are many, many distributions that satisfy log concavity, right? So Gaussian distribution will fall under it, uniform gamma, blah, blah, blah. Okay, so there are a lot of examples. And so this is where we started. Okay, so combine MTP2 with log concave just to make sure that it actually doesn't go off to infinity. Okay, so what can we say about the MLE? So what can we say about this function that maximizes the likelihood of seeing the data? So remember, this is the problem I'm trying to solve. This is now an infinite dimensional optimization problem because I'm maximizing over all functions that are MTP2 and log concave. This is now infinite dimensional, not like in the Gaussian setting where I had certain parameters that I'm optimizing over. So this is now the problem that I would like to solve. So under just log concavity, as I said, this has been studied, and the very nice result is known by Kuehl, Samworth, and Stewart, which says that the MLE, so that the estimator that maximizes that likelihood, that function, is in fact a tent function. Okay? So it is a tent function where the poles of the tent are over your data points. So this is a super nice result, right? Because it tells you that this infinite dimensional optimization problem can actually be turned into a finite dimensional optimization problem. Right? Because all I need is I have my data points, and I just have to optimize over the tent pole heights at these data points, once I know there is a tent function. Right? So this kind of, and in fact, it also turns out to be a convex optimization function, a convex optimization problem under log concavity. Right? So this infinite dimensional optimization problem of maximizing over all log concave functions was turned into a finite dimensional and convex optimization problem, where all I'm doing is just optimizing over these tent pole heights. Okay, because I know where to place the tent poles, namely wherever I have my data points. So now if I have n samples, it's an n-dimensional optimization problem. So this is a really nice result, yeah.
The function is a polyhedral function.
It's exactly, it's just a tent function defined by these heights. Exactly.
I was confused by the other thing.
By the 10 next to it, which is not so polyhedral. Okay, forget about this. This is like confusing. Yeah. Yeah. Okay, so now a question is, of course, and these are the kinds of questions that we want to answer, is, well, what happens if we do it under log concavity and MTP2? Is it again a tent function, right? And I will introduce another constraint on the next slide. So what is the shape of it? When does the MLE exist? Again, how many samples do I need? How does it look like? And then, of course, can we compute the MLE itself? Okay. So briefly, what is this LLC and why do I want to introduce it? So LLC is, again, here is a definition of MTP2 that we already saw many times. Now LLC is a stronger form than MTP2. And it's somehow, so it's a translation form of MTP2. So not only does this have to hold, but it has to hold for any points where I can translate my points by this vector 1, 1, 1, 1. Or I can translate, and I have to also be able to translate it by all of my y's minus 1. So in particular, if I choose alpha equal to 0, I get back this, right? But it has to hold for any alpha larger or equal to 0. So this is a much stronger constraint. Now again, why would anyone care about something like this? And So from a statistical point of view, I care about it because, for example, in the Gaussian setting, it means that these distributions are diagonally dominant. So meaning that the diagonal entries are large enough so that all of the row sums will become positive. And these have been shown to have a lot of computational advantages. Okay, so if your Gaussian is like this, you can compute all kinds of things fast. Okay, particular loopy belief propagation, etc. Will do actually very well. And now, from a mathematical point of view, why might it be the right kind of constraint, this LLC or this LLC constraint here? Well, because it's very close to concavity, right? So we're going to combine this MTP2 or LLC with log concavity. And it turns out that LLC is in the discrete setting is exactly what you would define concavity to be. Okay. So in the discrete setting, this LLC is actually log concavity. Okay. So that makes sense to actually look at this stronger constraint as well. And I'll be looking at both, right? But this is just a motivation for why to also look at this LLC constraint. Someone have a no? Still seems strange. Why would I care about it? Yeah.
No.
So we'll have, sorry?
But it seems like it's...
Oh, do I have larger or equal to? No? I think it's correct. Okay, so first of all, the question of when does the MLE exist? Okay, so before we showed in the Gaussian setting that the MLE, so this likelihood doesn't go off to infinity if we have 2 samples or more. So now a Gaussian MTP2 distribution is certainly a log concave MTP2 distribution, right? So I should expect that I need at least 2 observations. When I don't put, the Gaussian constraint onto it, because Gaussian is, of course, much stronger. And it's very surprising, I think, that in fact, if I have just MTP2 and log concave, I need just 3 samples for the MLE not to go off to infinity. Okay? So this family is much less constrained than assuming that it's Gaussian, but actually it is still very, very constrained because you only need 3 samples for it not to go off to infinity. And in fact, under LLC, well, this is a much stronger constraint. I just need 2 samples. So we can prove this result, but unfortunately, it doesn't tell us anything about the shape. Okay, so now we're still, so I told you when this exists, how many samples I need, but now I want to tell you something about the shape of the MLE. In particular, is it still a 10 functions? Let's start with something simple. I want to tell you what the support is, at least. Okay, so the support, so I have my samples, my points, right? So I know on the log concavity, it has to be convex, at least. And now, well, I have this MTP2 constraint, right, that the product of these 2 guys has to be smaller or equal to the product of these 2 guys. So definitely I need to have support here, because otherwise this will be, smaller than the product of these 2 guys. And I definitely need to have support here. Okay? So I need to take some kind of min-max closure. Right? So some kind of min-max closure convex hull is what you would expect. And so this is what I expect it to be, right? So the support should be the smallest min-max closed set that contains my samples. And of course, the intuitive way, or what we thought was true before, Bernd was always questioning it, but I thought it was true at the beginning, was that this is actually equal to the smallest, oh, sorry, what am I doing? So, yeah, okay, that you can just take the, okay, that I can, sorry, okay, so this is here is the smallest min-max closed and convex set, and here I'm just taking the min-max closure, right? So I have my points, I take the min-max closure, meaning I'm adding these 2 points. And now the question is, of course, can I just take the convex hull of my min-max closure? Does that give me the smallest min-max closed convex set that contains my points? Okay. In particular, is it still min-max closed, right? If I take the convex hull of a min-max closed set, is it still min-max closed? Well, I already said that, probably not. So it does hold in R2, and it does hold in the binary setting, but in general, that's not the case. And let me show you an example. So here is an example. So these are my 4 points in R3, okay? They are already min-max closed because, the minimum and the maximum of any 2 of these points is just the point itself. So this is already min-max closed. So I can take the convex hull, that gives me this polytope here. And now I have to give you 2 points so that the min-max closure is actually outside of it. And you can do that. So you can take this point here and 1 point here on the diagonal on this line. And you'll see that actually the maximum of these 2 is outside of the polytope. This is in general not the case that if I just take the convex hull of a min-max closed set, it will be min-max closed itself. I have to add a bit more. And this actually has been studied already in the 1970s. And how you get the smallest min-max closed convex set is actually very nice. There is a nice construction of it. So you do take the min-max closure, and then you project it onto any two coordinates, and then you just take the cylinder on top of it. Okay. So you take all of these cylinders and you just intersect all of them, and that will actually give you the correct support. So at least we can compute the support. Okay. So this is bigger than just taking the convex hull of the min-max closure. Okay, so this has been done, yeah?
So does that just like add in like this curved line over this upper facet on your triangle?
So in this case, it would be exactly this. This would actually be.
So that's like the only.
In this case, it's the only. If you do this construction, so I do the projection into any two coordinate planes, and I take the cylinder on top of it,
okay,
and you intersect it, this is what you get.
So in particular, it's a polytope.
So it is a polytope.
Oh yeah, it's a polytope.
Finite, the right-hand side is a polytope.
Yeah, okay.
Because I'm taking the cylinders over all of these.
Okay.
Okay, so we know the support. I haven't told you anything about the shape. So the first question, the simpler question I can ask is, well, I give you a tent function. Can you check that it is MTP2? Okay. So if I just do maximum likelihood estimation under the log concavity, I get a tent function. Well, if it is MTP2, it is the MLE. So can you at least check for me if the tent function is MTP2? Okay. So and this is actually also very nice. It's like, so all I have to do is I look at my tent function, and I look at the subdivision that this tent function induces. Okay. And all you have to do is you have to look at the walls in your subdivision, and you just have to check that they're bimonotone, meaning that you only have two directions where they differ, and in fact the product is smaller or equal to 0. So let me just say it in 2 dimensions. So the slope has to be positive, okay, in dimension 2. And otherwise, you just have 2 directions where they can differ, and the slope has to be positive there. So this is a very simple way of checking at least that a tent function is MTP2. Okay? Still haven't answered that every MLE is a tent function. But at least if I give you one, you can check if it is MTP2. Okay? So that's nice geometry that comes up. Now let's actually get to the question that we wanted to, right? Namely, is every MLE MTP? Is the MTP2 log concave MLE, is it again a tent function? And unfortunately, we don't have a complete answer to it. So what we know is that it is the case in R2, and it is the case in the binary setting. Okay. Then it is always a tent function, and this tent function can be computed, again, using a convex optimization problem. And that's what we did here. So this is just a log concave MLE, and this is the log concave and MTP2 MLE, and let me talk about this one afterwards. So you see already something nice. So here the data points were generated according to a Gaussian distribution. So you see very nicely that, with less samples, or with this few samples, log concavity doesn't give you anything that looks like a Gaussian. Whereas under MTP2, you already get something that looks very nice, like a Gaussian distribution, right? Just with this few sample points. And this one here is the MLE that you get under LLC. And so the nice result about LLC, and that's why I also want to introduce it, is under LLC, we actually don't have these constraints. So as long as you have any rational points, the MLE is always a tent function. Okay, so there we actually do have, we don't have it in RM, but for all computational purposes, the rationals are more than enough, right? There actually we can show that this is a tent function, and I do want to tell you what is actually missing. Why do we not have the complete result? Okay, so the complete result, so what this actually is based on is that in R2 and in the binary setting, and for LLC in the rational setting, in order to check that a tent function is MTP2, all I have to check is that the heights at the tent poles are MTP2. Okay, so if I have here a tent function, right, and I have some heights, then if I just check that these 4 heights satisfy MTP2 at these discrete points, that already implies that the whole tent function is MTP2, right? So I need it to be MTP2 on the whole convex hull of these points. So that only holds under in the binary setting or in R2, or for LLC it holds for any rational points. So it is really, and we know that it's not the case in general. So in general it's not the case if you're on R3, for example, that I can just check at the tent pole heights whether the function is MTP2 there and then just say that the whole tent function is MTP2. So So that's really what is missing. Okay? In particular, if I go back to this little example, this one here, right? So the problem is that, so in particular, over all of these points, right, every one of them will be one of the maxima or the minima. Any 10th function is MTP2, because the minimum and the maximum is just, actually happening at one of these points. But, so on the points, every 10th function is MTP2, but of course not every 10th function over this whole continuous polytope is MTP2. So that's really what is missing. Okay, so we need to be able to figure out where do we have to add in 10th poles, so that when you also check it there, then that's enough. Then that will actually give rise to the MLE, to the 10th
Is it
function.
clear, sorry, that it's either decidable or polynomial time, or?
If you can, so we don't even know if it is a 10th function, right? So if it's not a 10th function, then it means that I have to add in like an infinite amount of 10th poles for it to check if it is MTP2 or not. Right? So that's exactly, I think, the question. Also, like another question is where you're going there is like how many points do I have to add in, right? So even when we know there is a 10th function, I think here there is a bound, and here we don't know, basically. So we have a way of adding in, but we're adding in far too many, in general. Yeah, so we don't know like what are the bounds there. Okay, so let me end. So this conjecture is still open of actually showing that in general the MTP2 MLE is always the exponential of a 10th function. For LLC we know it, and this is kind of nice. So we have an algorithm which, if it outputs something that is MTP2, we know it is the MLE. But the conjecture says it should always be MTP2, but it might not, right? But then what is nice is that at least if this conjecture is not true, then we still have a way of giving you an MTP2 function, namely just I do it under LLC. Now then it might not be the MLE, right? But at least I can give you an estimator that is MTP2. It's just a more restrictive constraint. And I hope I was able to convince you that these total positivity or these MTP2 distributions, they really appear in many different settings where they are of interest to look at, in particular in finance and biology, etc. And they lead to really nice properties in the high-dimensional setting, right? You can actually do something with very few samples. And since it's so constrained, it actually already gives you very nice kinds of, for example, density estimates or very nice parameter estimates, etc. Okay, so here are some references. So in particular, one paper will appear today on the archive. This is the paper where I had at the beginning, where any MTP2 exponential family is convex. And in particular, we're here looking at the binary distributions and what it means. So thank you very much.
Okay, thank you. So time for questions and comments. Sorry, Akash.
In the case, like suppose you know that MTP2 MLE is exponential of a 10 function for like real points, right? And do you know that the space of such 10 functions, like the heights of over the poles, is still a convex polyhedron?
Exactly. So in this case, we know that this is a convex optimization problem. Exactly. So just checking, so just putting on the constraints that at particular points, the 10 poles are MTP2, that's convex. And that's why we can also solve it. Another open problem is actually to come up with fast algorithms for doing this. Okay, so just under log concavity, there have been like a series of papers now in computer science on the theoretical side, which actually came up with faster and faster algorithms for doing this. Under MTP2, we don't have yet.
Yes.
Question. Yeah, I think so in classical statistics, when people are doing non-parametric regression, they usually control the risk by computing the Rademacher or Gaussian complexity of the function class. Here, do we have some similar result that controls the risk?
Yeah, we don't have them. Okay. So there are a lot of open problems on even how large is this class, right?
Yeah.
So we don't know. And in particular, the conjecture would be that actually this class, that you should be able to get rates that are very close to parametric. Okay. That's so constrained that's what we're hoping to prove. Yeah.
Okay.
Because this is what it seems like, right? When you saw how much down the number of samples goes, it goes from p+1 to actually 2 to 3. Okay. So that hints at the fact that it could be close to parametric rates. Yeah, that would be very nice to show. So that's a big open problem in non-parametric statistics, right? Is how can you get shape constraints that actually get you down to the parametric rates? And this is one contender.
Yes, Olga.
Just a very simple kind of observation that the form in which you're looking to, say, maximize something was always log det plus maybe modification. But log det is trace log. So would that help sometimes? Maybe if you're looking and then, you can rewrite the logarithm of your matrix, as if you have a certain form there, which might make it easier for you to look at.
Yeah, I don't know. So it's certainly not in the non-parametric setting. So before, maybe if you have a hyperbolicity cone and you're doing it in the, where is it? So here in this setting, if you have a problem over a hyperbolicity cone and you have like some functions there, but then they're not determinantal anymore. So yeah, so I don't know what kinds of tricks can be done there.
It's just a reparametrization you might try to explore.
Yeah, it could be. Could be, in particular in the hyperbolic setting, might be interesting too. Thanks.
Okay. Any others? Well then, thanks Caroline, thanks to all the speakers. Reminder again, tomorrow morning the first lecture is at 9 o'clock, 9 a.m.